Okay, welcome here to my YouTube channel. I'm going to be doing YouTube video on me making my Cami videos again. So we'll start here on Cami. Welcome here. Today we're learning about refraction. So this is a discovery on refraction for what is refraction. The picture of refraction is a pencil in water. It bends. Maybe you put your hand in water. It looks like your hand or your arm is bent at a spot as soon as it enters. Now the pencil we know is not bent. If you pull it out, it's like a magic trick where the pencil's straight again. Uh, the reason this happens is because the light going into the water is bending, and so what we see is it bent. But remember, everything is just made up in our head. So it's not actually bent. It's just that the light going through the water is bent because light changes speed in water. And we can precisely predict this, as we'll see with our simulator. So if you click here, uh, actually, there will be a link on Google Classroom for you to click for this simulation. It should look something like this. And we'll start with the intro. And so the intro, we can click here and we turn on this laser. And we can move it around, and I'll show you some tools as we go. So our first question, what relationship exists between the incident ray and the reflected ray? Okay, so not the refracted ray, sorry. We're not talking refraction yet, we're talking reflected. And so this is the reflected ray up here, and this is the refracted. So reflected is off the water, like seeing your reflection in the water. Refracted is seeing your arm under the water. Okay, so what's happening under the water is refraction. What happens to the reflected ray? Well, let's use this. So we're going to grab the protractor and drag it. That's way is right in the center. And we've seen this before. And what it is, like if we go to 30, then the reflected ray is also at 30. Refracted, oh my goodness, is not at 30. That's weird. What if we go to like 60? Reflected is at 60, but the refracted is at 40. That's weird. And so that's what we'll write here. Okay, what is the relationship that exists between the incident ray and the reflected ray? They have the same angle. All right, and that is specifically from the normal line. And we talked about that last time. Okay, the reflected ray is going to have the same angle as the normal line. The refracted will not. Okay, and so that brings us to our second question. What angle of incidence produces a refracted, now we're talking about refraction. Refraction is the light that goes into the water, angle of 30 degrees. And so we can do this. If I just drag this and I look for 30 degrees, I'm looking down here for 30. Okay, as you can see right here, there's 30 degrees, nailed it. What angle of incidence? Remember, incidence is going in from the laser. Well, to me, this looks something like, I don't know, 30, 43, or 44. Let's do 43. And so I'll just write 43 degrees. That's the best way to write. All right, 43 degrees. What refracted angle is produced if the angle of incidence is 60 degrees? Well, we can do that. We did that already, right? 60 degrees gives us a nice angle of about 40 degrees. That's pretty nice. And so I'll just write that there. So we're trying to understand the difference between the reflected and refracted. Refracted is what goes into a different medium, and notice they don't have the same angle. Here we're going to be working with very soon, identifying this is material air and has an index of refraction n value of 1.00. This is going into water, which has a refraction n index of 1.33. Now, what if this was air into air? So we can switch materials quickly here. Air into air, there's no reflection off of air, which is kind of common sense, and there's no refraction because we haven't changed mediums, and so we go in at 60, we come out at 60. And so this is important to distinguish. We won't spend a lot of time doing this because this is a waste of time. Lasers will go straight if they don't change mediums. But what's interesting is if we switch to water, then we see that this bends, and we switch to glass is more dense than water. And this mystery stuff down here. We can play around here with these values, and we can see what's going to happen as the index of refraction changes as we go from air into a different source. Okay, so let's flip to the next page here. Notice how you've been using the protractor without even thinking twice about it. Where is it measuring 0 from? Do you think that's important? This is a rhetorical question. Yes, it's measuring 0 from this dotted line, which if you remember from our last lesson is the normal line. And so yes, that's very important. And this is such a wonderful protractor for this lesson because it measures 0 from the normal line. And so for 30 from 0, or 30 from 0 here, and here the 0 is at the bottom, and we haven't gone 30, right? And so just pay attention to where we measure 0 from when measuring refraction angles and reflection angles. Where do you measure your angles from? From the normal line. Just want to emphasize that. And now what's going to happen when we change the bottom to glass? So let's go from water is what we had to glass. And what is going to happen? We're going to see that the bigger the n value, or the index of refraction, the more the light bends. Okay? And so what I'm saying there is, if I change this n value here, as it gets more, you see the light bends more. As it gets down to 0, it doesn't bend at all. And the greater I make this n value, so index of refraction on the bottom is getting larger. You can see this is getting larger, and you see the light is bending more and more. So that's what I'm highlighting there. All right, and that's exactly what it says here. Okay, as the index of refraction n increases, light will slow down in that medium. Okay, so that's what's happening. And using a medium's index of refraction, this guy named Willebrord Snellius, greatest name of all time, Willebrord Snellius, he discovered this law, and we call it the Snells Law. And it precisely determines what angle the light will be reflected and refracted at. This is wrong. This should be refracted. What a joke. Who made these notes? And so he decided, or he figured this out. A lot of testing with this exact simulation. Now what you find is everything's going to work perfectly here because this is a simulation that is built around these laws. So it's always going to work. But Snell's Law Part 1 is stated here. You don't have to write this in you're going to notice that it's not precisely like this in your notes, and we'll get there. But this is where we start. Okay, I'm going to make a new video for the next part. But I'll just quickly summarize this. The big idea is we know the index of refraction, that's NR. That this one is NR. Okay, this is the 1.6 right now. And Ni is the index of refraction, the incident. Okay, this is Ni. Okay, index of refraction N, but incident. Index of refraction N, but refracted. Okay, the new medium has a different N value. Otherwise, remember, if they're the same, it's just not interesting. You might wonder, what if they're both water? Well, go ahead, do it. You have the simulation. And then notice here, we're going to be using sine theta r. R is on the bottom now, and theta I is on the top. So they kind of swap spots. Okay, we're going to do some questions with this right away. And so stay tuned and look to the next video over here. If you're watching on YouTube, that was pretty nuts. That was a fantastic segment there. Lucky people on Cami. Okay, we're going to go from here. For part 2. Okay, so let's do the next challenge here. Let's use air as the top medium and glass as the bottom medium. And then we'll determine the angle of refraction for a light ray if the angle of incidence is 45 degrees. We're going to start with Snell's law, and then we're going to verify observationally. And so let's go over here. We need air as the top, glass as the bottom. Okay, air as the top, we're good. Custom, no way. We want glass. Okay, what we need to pay attention to is the index of refraction. In air is 1, in glass is 1.5. This is the incident on top. This is refracted on the bottom. And so what we're going to write is this Snell's law as it applies. Okay, remember it's NR divided by NI. and r in this case is 1.50. We're going to divide that by ni, which is 1.00. Okay? And then that will equal sine theta I, but in this case, theta I is the angle of incidence, okay? And we know the angle of incidence is 45 degrees. And so sine of 45, then we divide that by sine theta, theta R, okay? So that's on the bottom here. Here we go. We know the refracted angle value and the incident value and the incident angle, but not the refracted angle. And so that's what we want to find. Boy, now this is some interesting math that we got to do here. What we got to do is swap these two values. Okay, I'll show you different strategies later, but that's good. Notice that this 1 really doesn't matter because 1.5 divided by 1 is just 1.5. Sine theta r divided by 1 is just sine theta r. It doesn't matter, okay? And so what we're left with is this. Sine theta r equals sine 45 divided by 1.50. Oh, no. There we go. Divided by 1.50, and we get the answer there of 0.471 dot dot dot. I'm not doing decimals, I'm doing dot 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 because I want you to leave it in your calculator. Leave it in and use the answer button later on. Okay, so we've got sine theta r is 0.471, but we're not done there. You cannot be done there because in order to finish off, you have to do this. Theta. So I'm not sure how familiar you are with trigonometry, but in this case, we have not solved. When you have the messy decimal, you have to use sine, oops, not that one, to the -1. Okay, inverse sine. We've seen this before, right? And this is where you punch in this messy decimal or you hit the answer button on your calculator, okay? And then you get the final answer of 28.5, okay? And this would be degrees. What is going on? 5 degree. There you go. And so that is our answer. And so we can verify this by putting in, we got glass and we said 45 degrees, so we go to 30, 45 right there. Boom. And we should see 27, no, 28.5. Wait a minute. Yeah, there you go, 28.5. With glass on the bottom, there we go. Okay, so if we do the same thing, but now we're going to do change the bottom to water, and what angle of incidence will we need? So let's change the bottom to water, and our angle of incidence is, and so water we got to pay attention to is 1.33, air is still 1.0, and so what we're going to do is the same thing. We're going to use our new formula, Snell's law, okay? And so in this case, we got 1.33 on top, and that's divided by 1.00. Again, doesn't, nice number. But this time we don't know theta I, and so it's going to be sine theta I, not one I, for incident, divided by sine, in this case, it is 20 degrees. Okay. Now to solve this, we just have to multiply both sides by sine 20. Woo, that was nice. Multiply both sides by sine 20. Wow. If that's not clear, I don't know what is. Okay. Then what we get is 1.33 times sine 20 equals sine theta I. Okay, and so then we get that sine theta I equals, what's that value there? 0.454 dot dot dot. I think technically this one would round, but I'm not rounding, I'm leaving the number in my calculator, okay? Because we're not done, because to finalize it, we have to do this. Theta I equals inverse sine. So sine to the -1 of our messy decimal 0.454 dot dot dot. Okay, and that gives us at theta I equals 27.1 degrees. Done. And that's our answer. So once again, we can verify this by going, this was water, and we said this was going in at 20 degrees. All right. No, we want it to come out at 20. We want it to come out there. Oh yeah, look at that. Perfect. 27.1. Bang on. We got it. Okay, now this part, determine the index of refraction of mystery A material. So what you do here is you go here to mystery A, and you can see, boom, it's purple. What is N is the question. You have to answer that. You're doing the same thing that, or you're doing similar things. You're going to use this law, and you're going to use your protractor, okay, to figure it out. So pick nice numbers. I would suggest that you use this one, because this looks like 60, and this looks to me like 20. Those are nice numbers. Okay, so 60 and 20 for your angles. Incident is 60, refracted angle is 20, and you know that the NI is 1.0 because it's up there. Okay, and then you're good to go, and you can figure out this one, mystery A. So go ahead and do that now. All right, that's the next video. Now we can keep going here. Okay, now if we that's weird. Okay, if we change this, we can change this to a wave. And so what this is saying is change the light source to wave. And so why don't we do that right now? And let's see what happens. This is pretty cool stuff. You see that the reflected wave looks the same. Essentially, it's just more dim, right? And the refracted wave looks totally different. Wider, right? Shorter wavelengths, but much slower speed. Very interesting. And we can see intensity here. We can see that when it comes in, 100% intensity, right? 100% of the light is there. And now we see that this is 60% and this is 39, the other remaining percent. So whatever's not reflected is refracted. It all goes somewhere, right? And what's interesting is as we change the index of refraction, let's go custom here. Okay, we can see right now it's 89. If we start at 0, oops, wrong way, 100% of the light's going to get through, right? But as we get more dense of a medium, we see that there's less intensity that gets through into the refracted medium, okay? Less intensity. And so what we can say here, so how does the angle compare? The angles are the same, right? We notice that right away. The angles are the same in a light ray and a light wave. Okay, and so this is whatever we're learning is true for big waves as long as just a laser, right? Lasers are really just waves. But what happens to the light intensity as the index of refraction increases? The intensity decreases. That's what we observed, right? And what happens to the wavelength of the waves when they enter a slower medium? What you see about the wavelength, they are smaller. You see wider waves and tighter waves. So the wavelength becomes smaller in more dense mediums, higher N values of index of refraction. Okay, and so Snellius, Willebrord Snellius, he noticed this and he said there's a correlation, a relationship between the wavelength and the index of refraction. And it looks like this: the index of refraction and R on the top, and the incident index of refraction on the bottom. is equal to the new wavelength, no, the original wavelength divided by the new wavelength, okay? Theta r is the new wavelength. And so this relationship is also true, okay, correlated with NR and NI. And then he also figured out that then he could figure out the speed of the refracted waves. Wow! This index of refraction thing is pretty awesome because this NR and I, if we know that, we can figure out the relationship between the wavelengths. We can also figure out the angle of reflection or refraction. And now we can also find the speed, okay? How the speed is going to change. And since we know light speed, we know it quite accurately. We know it's 3.0 times 10 to the 8 meters per second, okay? And we call it C. And this is important. This is going to come up. And we know that the index of refraction in air is 1.0003. And so the speed of light in air is virtually the same as the speed of light in a vacuum, okay? And so we don't have to change it. That's why we can go 1.00. And yes, that is the speed of light in air. It's basically the same as in a vacuum. And we can use this to predict the speed of light in water. And so let's see if we can predict it. So we just need to remember, if we have this, we just need to remember, well, we know the index of air is 1. What's the index in water? We just look, we go to water, and it is, the index is 1.33. And so we can use this now because we know the speed of light in air. And so if we use our equation, we can go here and say NR, in this case, that's the water's index of refraction is at 1.33. And NI is 1.00. And that equals VI, the angle of incidence, no, so the speed of light in air, in the incident, no, not 1.33, 3.0 times 10 to the 8. Okay, and we have to divide that by, no, gotta do this bracket, close bracket. Now divide that by VR. Okay, now once again, we can do this swappity swap thing, right? But I'm going to show you a cool trick. This Snell's law can also be reversed. We can write it just as accurately this way. Ni divided by Nr equals V, and this time we have to do R on top divided by Vi. Okay, we can write it this way. We can flip it. As long as we flip both pieces, that's all good. Okay, now we got I on top and I on for N and R on bottom, right? We flipped N. We also flipped the V. If we flip both of them, then we're okay. And so if we would do that, then here we could say 1.00 divided by 1.33 equals the R divided by 3.0 times 10 to the 8. And this is just nicer because now we can just multiply by 3e8, right? Just doing a shortcut, times 3e8 on both sides, and then we're good to go. And then we've solved for VR. It's not fun having them on the bottom. And so don't ever have it on the bottom. Just flip your equation around. Pick which one you want, okay? It doesn't really matter. Well, it does. Choose the one that's more convenient. As long as you flip both pieces of the law, then you're good. And so when you do this, you get 3 times 10 to the 8 divided by 1.33. And what you get is, sorry, let me get this here, 2.26 times 10 to the 8. And this is in meters per second. Okay, that's just how it is. All right, and so this is our final answer. We've predicted the speed of light in water. This is significantly less. It's still very fast, but it's a lot less than the speed of light. And so now we can go to the more tools page, okay? And we can, oh, where is that? That's down here, more tools. And this thing has a speedometer. So we can turn this on, we can get the material to be water, and we can check this out. We've got the speed of light, 1c, that's 3 times 10 to the 8. Remember, c is 3 times 10 to the 8. And here in water, it's 0.75 c. Why don't they just tell us meters per second? Well, they don't. And so you just have to do a little bit of math. 0.75 c means 0.75 times 3 times 10 to the 8, 89. And when you do that, you get the speed. I've got it written down here, 2.25 times 10 to the 8. Oh, that didn't work at all. There we go. Meters per second. And so this is basically exactly what we got here, right? It was a little bit off, but we got the same. We predicted it. We predicted the speed of light in water. And so what I want you to do here is use the speedometer to figure out the index of refraction of mystery A. Okay? And then compare the new index of refraction you get with your first value. See if you get the same thing. And so what you got to do is figure out, go to mystery A and see, okay, what's my new speed? It's 0.41 c. Okay, and so you could figure out what 0.41 c is in meters per second, and then use Snell's law. Okay, but part 3 of it to figure out what nr is, because you know ni is 1, you know vi is 3 times 10 to the 8, and you can find out what vr is using the 0.41 c, and then find a new index of refraction. See if you can get the same index of refraction you got in the first time. That'll tell you if you've done something wrong at some point. Very good. Last video will be over here. All right. Boy, it's been a wild ride. Okay, we're almost done. Last part where we bring it all together. Bonus content. This has all just been leading up. Oh, I did not mean to do that. This has all just been leading up to the total Snell's law, which is coming up here. Okay, so hopefully you haven't spent too much time writing this down and thinking about it, though you should be thinking about it quite a bit. Here we go. Okay, let's bring this all together. Here's what we've learned. NR over NI, okay, the two index of refractions can tell us the difference between the angles. It can tell us the difference between the wavelengths, and it can tell us the difference between the speeds. Well, if this equals this, if A equals B and A equals C and A equals D, then can't we say that B equals C and C equals D and B equals D? I don't know if that made any sense to you, but if it did, then you'll see that the natural conclusion of saying these three things is that we can say it in one smooth statement. And this is the complete Snell's law. Okay, this is what Willebrord thought, that when he put this all together, he's like, this is awesome. I got to write this down and tell the world that, in fact, this is not working. I wanted to erase that, but whatever. In fact, if you know the index of refraction, you know the angles, the wavelengths, and the velocity. But in fact, if you don't know this, that's not a big deal. If you know the change in wavelength, you also know the change in speed. And you know the change in angles. Okay? And so they all are connected. And so you don't need any one piece, you just need a few of them. And so this is pretty powerful stuff. And so I'm going to show you how we can use the Snell's law to determine the angle, the index of refraction of mystery B. Okay, and I want us to do this 3 different ways. Okay, and these 3 different ways would be this. So we're going to go here to mystery B, and here's the best part of, well, let's start with speed. Okay, we know the speed coming in is 1c. What's the speed in mystery B? 0.71 c. Okay, and so we've got, and that's all we need to know. What are we going to use then? I gotta erase this. This is a bit laggy doing 2 live streams at once. What are you gonna do though? I don't think there's any other option. Okay, so if we know that, what did I say, 0.71 c? Okay, if we know the speed, we know v, right? We know vi is 1, we know 1c, we know vr is 0.71 c, and we know the index of refraction is 1.0, right? Then we can find nr. And we can ignore this stuff in the middle. We only need 2 pieces. So we get to pick which pair we want. Which pair is convenient? And so that's what we're going to do. And so let's do it. What this looks like is we're going to use this section. And oh, I do also want to think, oh, right, the one we circled is on top. And so we leave it that way. That's perfect. Do NR divided by NI equals, oh, we don't need NI. We know what NI is, 1.0. Index of refraction in the air equals 3 times 10 to the 8, right? That's the speed of light in air divided by 0.71 times 3 times 10 to the 8. And what do we get? We get the answer. I should do this underneath. And R equals 0.41. Pretty sweet. So you just punch this in your calculator. The speed of light divided by 0.71, because that's what it said it was the speed, and we can figure out the index of refraction. Well, we can do it another way. Okay, check this out here. On more tools, I know you've been using this protractor, but I wanted you to get used to measuring from the normal line, and that's why I didn't show you this function, which doesn't exist in the intro. Okay, so if we put a 45 degrees in here, we can see a 30.3 degree angle of refraction. So another way, I said do this 3 different ways. Okay, so way number 2 is this. I'm going to put in, I want to use this part. Okay, we've got the 2 angles and we've got NI, and so we want NR. And so let's do it. NR divided by NI. Oh, I did it again. 1.00 equals, in this case, it's sine of 45 degrees was our angle, divided by sine of, what was the refracted angle? 30.3. Just like that, and you can get it. So you can do that, and then you'll be done. Do it one more way, and the way I want you to do it this last time is change the index of refraction on the top to something else. And doing that is going to be quite interesting. And so try that way, and then you'll be done.